just want to make sure real quick that you have either paused my face on Twitch and you can still read the chat. Can you see the chat by
I can't
chance?
see. I should actually get on so I can see the chat.
Yeah. Do you need the
yeah.
link?
I should actually still have it from last time.
Okay. Guys, there's Dr. Emily Levesque. Everybody's saying hi, hi, hi.
Hi.
And heart attack. That was my fault. That was my fault. Usually I'm really good about adjusting that. I didn't have my volume mixer up. That was my user error. Sorry, guys. It is her. Yeah, because we all watched your talk at the Perimeter Institute.
Oh, cool.
Which was absolutely amazing. You did such an awesome job. We were maybe making fun of the audience a little bit, though.
No, you know what? They were doing a great job. They were extremely attentive. They asked really great questions, so that was super fun.
Yeah, they seemed let's see. Well, yes. I'm just going to say that they probably again, since this is completely off the record and you don't have to be formal here at all. Yes, we were yes, a lot of them were not. This should just not pan out on on the audience ever. Even with the Hubble lecture series, they do it all the time, and I'm like, there's nobody there.
It was kind of funny the way Perimeter set up. Is it was a full room of people, and they actually have overflow rooms there now. So there were a bunch of people watching. I guess they set up a screen in the cafe outside. And that seems like the place to be because they can watch the lecture. I guess they can't ask questions, but they can watch the lecture and they can like order a beer. So I think we filled the overflow rooms too.
Oh,
and
yeah,
apparently the party rooms were the place to be.
Yeah, because it was an amazing talk. And it was so funny because everybody in my chat was saying the same thing that I've always said about you is that your energy. And then the guy, of course, says it. And I'm like, thanks. Because we were just saying that. Like someone said her energy about talking about stars and all of this stuff is just so infectious. And the guy said the same exact thing. But yeah, so we watched your and when was that? That was relatively recent, wasn't it?
That was March 8th, I think, or around then. So a couple months ago.
Yeah. So that's not too far off.
Yeah.
Someone said I would most definitely be one of the people watching the cafeteria having a beer. It's okay.
Yeah.
That's sometimes the best way to listen to astronomy stuff. And someone says, I don't like, okay. So usually what happens is, and this is a little bit different from the first time we had you on here. It's much more casual this time. Because when I have guests on here nowadays, like I kind of moderate the questions from the chat about anything that they have, anything regarding, if they want to talk about GMBs, or GRBs, sorry, gamma ray bursts, and also talking about stellar evolution, which you guys, her forte is these higher mass stars, right?
Yeah.
Yeah, so the really cool ones. Not saying that our star is not, but it's not as eventful as the ones that she knows about and studies. Those are, in my opinion, much more fascinating.
Yes.
So go ahead and give an introduction to yourself. I know you just have a new book out too, so go ahead and just introduction.
Yeah. So I'm an assistant professor at the University of Washington, and my research in a nutshell is I study how big stars die. So a star like our sun is awesome. Our sun is great. I know people who their entire research focus is the sun, and it's fascinating because it's so close that we can observe a ton about it. But it's a fairly garden variety type star. Its mass, its temperature, its age, everything about it marks it very much as a typical star. So I'm interested in the much more massive cousins of stars like our sun. So these are stars that are 8 times our sun's mass or more. And that hits a transition point where stars are able to evolve in a very different manner and evolve much faster. So a star like our sun is about 10 billion with a B years old right now. Massive stars live on the order of 10 million with an M years. And these are the stars that actually evolve and then collapse in on themselves and bounce off and explode as supernovae. So what I'm specifically interested in is sort of those late steps of stellar evolution leading up to the explosion, leading up to the supernova itself, and understanding how stuff like where the star was born, whether or not the star has a binary companion, exactly how massive it is, how all of those things affect the type of explosion that it winds up making. So sometimes I observe stars directly. Sometimes I observe the galaxy where a star has just exploded to see if you can sort of do forensic analysis on the explosion site and learn some stuff about the star. And sometimes I try and theoretically model or mathematically model them to figure out what we're doing. It's a really fun mix.
And so how many galaxies are you able to observe? Because obviously these supernovae explosions only happen so many times, in a given, 100 years, maybe one every 70 to 100 years in a galaxy, right?
So in a galaxy, yeah, usually our galaxy, we expect we should have about one galactic supernova every 100 years or so. And I mentioned this in my talk too, but it's been 400 years since our last galactic supernova. So we should have expected to see one by now, and it would look amazing. Like that nearby in our own galaxy, it would get so bright that you'd be able to see it during the day. It would last for 2 weeks. It would stay that bright for 2 weeks, and then slowly fade away. So that would be really fascinating. But most of the supernovae that we observe are in much, much more distant galaxies. We observed one not too long ago in a neighbor galaxy. We can get a handful from the very most nearby ones, and most are much farther away. So if we're lucky, we can pinpoint where in the galaxy the supernova happened. A lot of times we're stuck with looking at the galaxy as a whole and trying to guess what about that galaxy corresponds to the properties of the star before it exploded. But we can get most of them. For most of these supernovae, we can pinpoint the galaxy where they happened and try to backtrack and study them.
So do you ever get tricked though? Does the universe ever trick you and say like, hey, I'm going supernova, but not really?
Yes. I love these stars, and I'm actually working on these right now. There's a specific subtype of star known as luminous blue variables. So these are stars that are really massive. The estimate is like 50 to 80 times the mass of our sun. We're incredibly boring at naming things in astronomy. So luminous means they're really bright. Blue means they're really hot. Variable means they change a lot. And some of their changes can mimic what looks like a supernova explosion. These stars will occasionally puff off or fling off huge amounts of mass. And we honestly still don't really understand why. But when a star flings off mass like that, it will temporarily appear to get really bright. And for really distant galaxies, the only way that we can see a supernova happening is you go from nothing to a star suddenly appearing. And what looks like a star appearing is actually the bright light from a supernova suddenly turning on.
Right.
We will see something get bright and go, oh, hey, it must have been an exploding star. Name it as a supernova and sort of move on. But then every once in a while, that supernova will fade away and then come back, because what we were really seeing was a star that erupted, exploded, and then erupted again, or moved back to its normal temperature and normal brightness.
So you're actually not seeing any kind of supernova going on at all?
No. We think we might have gotten lucky about 6 years ago and had a star that we originally mistook for a supernova. It turned out it was just erupting. We think we saw a couple eruptions and then the star's actual death explosion. And I think there are still people monitoring this thing to try and say for sure if it's really gone or if it just got really dim. But that is one of the tiny handful of exploding stars where we've actually gotten a good look at the star before it died.
Yeah. And so
it's rare.
Someone said, I see that 10. I'm going to ask that later because that's a good question regarding, and again, so her emphasis is going to be more about these, stellar evolution, especially these high mass stars. And the gamma ray burst, that's another thing that she's very knowledgeable about.
I'll take cracks at any questions though. If I don't know, I'll let you know.
See, that's what I do. But I don't have that PhD like you do, which is well earned and deserved. So, and that book too. I that's a book for me. And again, guys, like you guys can get that book. It is not designed for. It's for my chat, you guys would love this book. So
there's a couple, just so that people know what we're talking about. And I have it. So I wrote 2 books last year, and they were published by the Institute of Physics, IOP publishing house. And they were published with that publisher and along with the American Astronomical Society. So one was this one. Mm-hmm. So this is a book that I single authored. So it's just about red supergiants, which are one of my research specialties. And these are stars like Betelgeuse that are very massive, that are very cold, that are possibly getting ready to die as supernovae, possibly getting ready to turn into other stars before dying. And it's basically just a summary of everything that we know right now in the field. It was really fun writing it because I had to do a bunch of side research on aspects of red supergiants that I didn't work on very closely. So now this is a super useful reference book for me because I wrote down everything in one place and now I can find it again.
I know that is useful.
And I'm hoping it's useful for other people as well. And then the other book was this one. I see somebody's putting up the links in the chat. So this is a textbook that I co-authored with Henny Lamers, who is a professor of astronomy originally from the Netherlands. And it's based on a course that both of us have taught here at the University of Washington, and is just graduate level introduction to how stellar interiors work and how stellar evolutions work. Revolutions. It's been a long day.
No, you're fine. No, like this is how I talk normally, and this is why Twitch is amazing because you're not. Yeah, I'll say supernova and then mean supernovae and all kinds of stuff. Yeah. So can I see the title of that book again? Because that's your recent one. That's the one I was like, you put this out.
They actually both came out at about the same time, which was December of last year.
But you had this one in January, right? Like this one actually.
Yeah, this one came out like a touch later. Yeah.
Yeah. And so it's understanding stellar evolution.
So we had a lot of editing to do.
Yeah, that one's. I'm super excited about both of those, and a lot of people in my chat would be able to understand that content within, even though it is a higher level course.
It's graduate level, but it would be a great textbook for like advanced undergrad work too. And it was wonderful working with Henny. This was originally his class and his lecture notes. I originally came onto the project as an illustrator, actually, making really clear plots and sort of figures for the book, and then became a co-author. But we both subscribed to the idea that you want something to be as simple and understandable as possible. And there's a lot of moving parts and a lot of details to consider when you talk about how a star evolves. So throughout the book, we always try to dig into the really nitty-gritty physics, but then back up and say, what does this actually mean? Is the star getting brighter or dimmer? Is it getting hotter or colder? Why? And trying to make it really clear.
Yeah, and I'm excited for both of those. Those are actually going to be really good. And a lot of people ask, like, what can you read? How can you get back into this? And those are good ways, especially for a lot of people in my chat. There's a lot of people that are very knowledgeable about astronomy in here. Sometimes when I'm having a brain derp day, they're great. They're great. So right now we actually have Betelgeuse, and you say Betelgeuse, so we were talking about this because Sharon, Karen, this is how this works in space. But I definitely don't say Betelgeuse, and everybody's like, you're saying it wrong. And it's Betelgeuse, Betelgeuse. It depends on where you're from. But someone says, let's see. Well, actually, that's a good question. Someone was wondering about how difficult the math is at this level.
This goes through calculus and differential equations. The particular aspects of astronomy that I work on, we don't use a great deal of linear algebra, but if you go through like a quantum class, you end up needing linear algebra, but it's pretty gung-ho. I will say that our textbook uses a good amount of algebra trig, calculus, differential equations. The Red Supergiants book actually has, I think, only a tiny handful of equations in it. And that's partly by my own design, that this was meant to be a summary of what we know about these stars right now. So I would much rather describe something in a paragraph than put it in an equation. You can write out an equation and be like, L equals 4 pi r squared sigma t to the fourth, and sure. And
right.
There's a tendency, even with students who can be really, really mathematically sharp, to kind of lean on the math. And what I'd rather do is hand somebody that equation and tell me, what does this physically mean? If you have a star that's cooling off and getting bigger, what is that telling you? If you have a star that suddenly got a lot brighter, but its temperature hasn't changed, what does that mean? And I prefer the explanatory method because you actually have to understand it. That you have to really have a good understanding if you can go from an equation to explaining things in words.
Right. No, I agree. And that's why you're amazing at what you do in these lectures that you give, is you do such a good job at explaining very complex things. And that to me, and a lot of people in here would agree that that's super important. Because you can get so many teachers that can explain all the formulas and everything that's going on, but they're not going to engage the students. And That's a big problem. So someone says, will we know where to look for Milky Way supernovae based on neutrino detectors before we see it? I know.
So that's a really fun question. So to explain to people what they're asking, just if anybody's not, first of all, can you still hear me? I know my internet just kind of.
Oh yeah, no, you're great.
Okay, cool. So we would typically detect neutrinos as the first sign that a supernova has happened. I don't think that the neutrino detectors we have are very good at telling us where the neutrinos have come from. They will detect a neutrino being absorbed or collected in the detector, but they can't be pointed very well. We can't say, oh, the neutrinos came from over there. So our best bet for galactic supernova is going to be the light from the supernova itself. And it should become very obvious very quickly.
Right. That so right now, like I said, and this is what's so cool. So you've updated, because I've followed your lectures, because even when you have ones, I usually am listening to them live, even if I'm not live on here, because I sign up for them.
Thank you.
Well, no, it's amazing. The way you talk, like it's one of those things that I look up to and strive to do it here on Twitch. There was something that you had in your previous lectures when you were talking about Betelgeuse, for instance. This is one that we're hoping goes supernova. It's obviously very close towards the end of its life, and we're hoping in the next several hundred years that it does. And that's kind of, if I don't know if you can actually see the image on this screen, it might be paused, and that's okay, because overall I just really need to be muted. But I have Betelgeuse, and the representation that they have in this space sim, this simulation is perfect for what you just showed at your lecture in the talk at the Perimeter Institute, because it describes why it looks like, everybody can tell you, I don't remember the name of the candy, like a Ferrero, I forget what they're called. They're chocolates.
Ferrero Rocher or something like that. Yeah.
and everybody's like, oh, it's a cheese ball. It's like, it doesn't look like a normal star. So why does it look this way?
Well, so that illustration is actually, it's okay as an estimate of what Betelgeuse looks like. And I don't think that's anybody's fault. These are very hard stars to model. But if we actually, there's people that have actually managed to image Betelgeuse. It's one of the only stars that's close enough that it doesn't look like a point. It actually looks like a little tiny disc. And the images just sort of look like orangey red discs. But if you try and model what it looks like, Betelgeuse is huge, and it's very, very cold. So its surface appears as red. This is something that I love telling kids at astronomy lectures, because they always get this backwards. They think that hot things are red and cold things are blue, because they're used to like the faucet in their house.
Right.
And every faucet you've ever seen is a lie.
Yep.
And the hotter something gets, the bluer it gets. So the red star is a sign that this star is pretty cold on its exterior. Its outer temperature is 3,400, 3,500 Kelvin, which is cold. That's still very hot to us. But for a star, that really is quite frigid. And as part of that, it means that the star's outer layers are really puffed up. They're very puffy. They're not very dense at all. And you get these really fun features on the surface of a star like Betelgeuse. On the surface of our sun, you'll see these little things called granules. And what you're seeing is basically the top of a convection zone in the sun, where hot material is coming up and then cooling off and falling back down. So on the sun, if you were to turn this over and look at it this way, it would be smallish. On Betelgeuse, they're huge. They're almost the size of the star itself. You maybe have 5 or 6 cells like that you can see on the surface at any given time. So it looks very dark red. You see these sort of few cells of boiling material, and the whole star kind of looks like it's boiling away as those cells carry hot material out in the center, and then cool material falls back. So it's pretty cool.
Yeah. And how far away is, and with the Gaia, the second data release, were they able to get more of approximation on how far away this is? I've seen so many numbers with Betelgeuse.
Yeah, I actually haven't checked Betelgeuse yet. And there's tons of groups that are working on measuring very careful distances to a star like Betelgeuse. And if I had to guess, I think Betelgeuse is probably too bright for Gaia to observe. Have you talked about Gaia on here yet?
Not in depth.
Okay, yeah. So
you can,
Gaia
please.
is Awesome. So Gaia is a space observatory that was launched by the European Space Agency back in 2013. And what it's doing is monitoring over a billion stars in the Milky Way and observing each of these stars about 70 times. And the whole purpose of this is that it's trying to study each star's very precise position and motion. And it means that we'll wind up with this amazing 3D map of objects in the Milky Way. We usually think of it as being limited by how dim stars are, because we had to pick a particular size and sensitivity for the telescope, and we decided that it couldn't see incredibly dim stars. There's also stars that are too bright. I haven't checked this for sure, but I would guess that Betelgeuse is too bright for Gaia because we can see it with our naked eye on Earth. But they just put out what they call their second data release. So it came out on April 25th of this year. They basically released this immense amount of data that people could just go in and play with. And astronomers all freaked out. And we were able to use that to answer some really long-standing questions about individual stars, about clusters of stars. And I mean, we're still kind of exploring through that data set, but even something as simple as being able to tell exactly where a star is and exactly how it's moving is really valuable.
Yeah. And actually there's a lot of good questions coming from this. And this goes right in line with what again, we have to study stars to understand more about them. So is there a theoretical maximum size? And I'm guessing I'm just going to just throw in, let's say, mass.
Yeah.
Mass limit for a star.
There is, and it changes depending on who you ask. Right now, if we were to sort of make a star right now in the Milky Way, we think that they probably couldn't get a lot more massive than about 100 to 300 times the size of our sun. And I know that's a huge range, but 100-ish times the mass of our sun is about the most massive star that we think we can make. If you go back to what the universe was like right after the Big Bang, the chemistry of the universe was very different. And the physics dictating how stars form and evolve and behave was different. So we think that maybe back then we could have made much more massive stars. But usually when we're trying to simulate a group of stars and pick a maximum mass, we go with around 100.
There you go. Someone says, yeah, it's all relative. So someone asked, how is, and this is not a bad question. How is navigation documented in space? On Earth, we have north, south, east, and west, but in space, how do you know what direction you're headed? And in addition with the Z-axis.
That's a really good question. So I'm not a very useful reference for navigating in space because, to my great disappointment, I've never been. But this is how they actually navigate something like the space shuttle or the missions that went to the moon is really interesting. And they did use star charts as part of their navigation. When we're just trying to find an object in space, we observe space from here as a 2D image, basically. So we just need to deal with up and down and left and right on the sky. And how we define that gets a bit more complicated. But we will figure out where something is located in the night sky and then use other tools to figure out how far away it is. Sometimes we can use something like parallax, which is a tool that Gaia uses a great deal. You can do parallax if you just, look at something with one eye and then the other, and you'll see that things near to you move a lot as you look with your left eye versus your right eye, and things that are far away don't move that much. We basically do a meta version of that with Gaia and can tell the distances to relatively nearby stars within our own Milky Way. At greater distances, we can look at things like how fast an object is moving away from us. Since the universe is expanding, if something's very far away from us, it appears to be moving away from us at great speed. So we'll use other tools to figure out the distance to something. Determining distance in astronomy is actually pretty complicated, and we have a bunch of different mechanisms for doing it. So to find something with like a telescope, we just settle for position in the 2D sky.
Yeah, parallax is a huge tool. Someone said, I've read that the equatorial regions of Sol rotate faster than the polar region. Yeah, it's about, I think, 25 days at the equator, or maybe 27.
It's 27 at the equator.
And then like 29 at the poles?
The equator is actually faster than the poles.
Right.
So yeah, 27 and 29, I think that sounds about right.
Yeah.
So the mechanism that causes that, it's partly a side effect of the fact that when you imagine a star, the first thing you imagine is just a ball of gas. And it's tempting to think of it kind of like a bowling ball. And what it really is a relatively diffuse ball of gas. So you can easily imagine a scenario where the inside of the star could be spinning really fast and the outside could be spinning fairly slowly, or different regions of the star will be rotating at different rates. What's fun about the fact that the sun has a different rotation speed at the equator and the poles is that this is part of what gives us things like sunspots. Because the star is spinning like that, you actually wind up tangling the magnetic field lines in the star. And that's why we see some of the magnetic activity that we do from the sun.
Yeah, and we're still trying to learn why. I think actually there was a double AS press release today about the corona. Yeah.
Oh, really?
Yeah, but we're going to learn more about that with the Parker Solar Probe, right? How we're going to learn about why its atmosphere is hotter than its surface. That's a big mystery. We don't understand why that happens with stars, right?
Sorry, say that last part again.
So why their atmospheres are hotter than their surface?
So the atmosphere of a star on its own usually isn't hotter than its surface, but something like the corona the fact that the corona is way hotter, we don't understand.
Yeah, and that's one of the things we're hoping to learn, I think, with the Parker Solar Probe about our own star. There's so many good questions. Wow. Let's see. So, let's see. There was more up here, and I just had to pause it. Sorry, I had to pause the chat.
No.
Where is this one? So will TESS be able to help in identifying stars for future supernova events?
We think so. So I haven't done much work with TESS directly, but I've had conversations with collaborators that are dying to use TESS data as a means of studying supernovae and studying the types of stars that could make them and stuff like that. So very much probably.
And so
I'm looking forward to seeing what they find.
Right. And going back to the supernovas that like to fake us out, where we think they're actually going supernova, but they're having these eruptions. Mm-hmm. What are those eruptions? Are they like similar to, someone just said a solar mass ejection, which you'd probably, I don't know if you mean like a coronal mass ejection, or what are these eruptions? Have we figured any of that out?
We really haven't. We know that they're hurling off some impressive amount of mass, but we don't know why they're doing it. We don't know if it's because the star suddenly becomes unstable, if it gets too hot or too luminous to remain in equilibrium, if the star is being disrupted by a binary companion. We're really not sure.
Yeah, so I think that's another mystery. Stars are pretty mysterious. Someone says, what is the range of percentage mass of a parent star left in a stellar black hole directly after its formation? That's going to vary, isn't it?
It's going to vary, but it's less than the mass of the star. So if we take, I won't pick Betelgeuse because Betelgeuse is probably not massive enough to make a black hole. But if you took something like a star that's 30 times the mass of our sun, it is going to shed lots of its mass. A lot of its outer layers are going to get blown off by little eruptions, by winds. Stars actually have winds at their surfaces that help carry away material. So the star will be born with 30 solar masses worth of material, but not every bit of that mass winds up going into the black hole. The black hole will be a lot lower mass.
There. So let's see. I was trying to actually show like how the solar winds get like peeled off of this thing, but it wasn't showing well. So let's see. Have you spotted any difference in? Joe obviously was on your Twitter.
Yes.
Have you spotted any difference in behavioral patterns of spiders this year?
Yeah, I can explain this. Okay. So we had a small spider problem in our department last year, and Jamie Lomax, she's a postdoc here right now. She's actually moving on to a faculty position this coming fall, but she was working down the hall from me and she had spiders like pouring onto her laptop. And somebody at some point mentioned to her on Twitter, a guy named Alex Parker mentioned to her on Twitter that these spiders might follow laser pointers. And it turns out some subspecies of spiders, what are called jumping spiders, will follow laser pointers because they have very good visual acuity. This is different from like the spiders that you see spinning webs, because they just sort of spin a web and wait. They don't have to hunt. But he mentioned this to her, and I had them in my office too. And I like looked around my desk right here, and I was like, all right, I have a red laser pointer that I use for class. I have a green laser pointer that I use for pointing at stars at night. I wonder which one it'll chase. And to me, this just seemed like the obvious science step that you take.
Absolutely.
So I had a spider on my wall. I filmed it chasing both laser dots. I put it on Twitter. For some reason, people thought this was amazing. We wound up pinging some spider scientists on Twitter, and then they found us and started explaining what we were seeing. What I actually kind of love about it is that the scientists took it and ran with it. And the scientist we actually wound up getting was a guy named Nate Morehouse, who I think he was at the University of Pittsburgh. And he was explaining that spiders actually have really excellent visual acuity. Their eyes work like little telescopes. They have like a back lens and a front lens. And this evolved into the spider scientists and the astronomers talking and like trying to figure out, well, what can spiders see? And people did the math and figured out that these little spiders can see the moon. Like their vision is actually good enough that they could see the moon in the night sky, which you wouldn't expect for something like yay big. And it all culminated in Nate Morehouse actually coming and giving a research talk here at University of Washington. And it sounds really weird. Like, why are you going to invite a spider scientist to talk to a astronomy department? But it was unbelievably interesting because he talked about the optics of how spider eyes work. And he specializes in how spiders perceive color. And I think everybody was sitting in the audience going, God, maybe we could design a telescope this way, because it's a different design than how a telescope works. So it's kind of fun to watch different branches of science meld and see what comes out of it.
Oh yeah.
But yeah, they asked that because it's been about a year and the spiders are back now. So we're playing the laser pointers again.
Yeah, I watched that. That's on our Twitter, guys. It's absolutely hilarious.
Yeah.
So Joe had a good question. So KY Cygni, is that the biggest star we know of? And has that taken over UY Scuti?
KY Cygni, by our measure, is, if not the largest star, then one of the largest stars that we know about. As we observe more red supergiants, so red supergiants they're physically the largest stars in size that we know about, like in radius. And as we study more red supergiants, odds are we're going to find ones that are larger. But right now, KY Cygni is pretty close. There's another star in the Large Magellanic Cloud, so one of our sort of satellite galaxies, that we also think is quite large, but trying to measure its temperature is a little bit complicated because it's surrounded by a lot of stellar dust. So that one might beat the record, but we won't know for sure until we've gotten a really careful measure of some of the other physical properties.
And so, yes, because usually, when I try to show people the differences in size of these stars compared to say our star, they're unbelievable. So like a lot of people think that the largest star to date is still VY Canis Majoris. So KY Cygni would trump that.
I think so, yeah.
Yeah. And so
VY Canis Majoris is also hard to study for this same reason, because it's really dusty.
It's really, yeah. So is it because of all that solar wind that's leaving it?
It's because of the star's wind or other ways that stars have of losing mass. Like, for example, we think that these stars might pulsate a little bit. So as part of pulsating, they're sort of puff off layers or shells of dust. And then that the material from the star will condense into dust around it and kind of shroud it. Somebody's asking if stellar dust is very hot, and it's not terribly hot. So we mostly see it. It shows up as bright in the infrared. It's fairly cool. So we'll see it sort of veiling a star or making it look not quite as bright as it actually is. And that can sometimes mess with an estimate of its color or its brightness or luminosity, things like that.
Yeah, someone just said, according to Wikipedia, VY Canis Majoris is ranked number 7. I don't know what Wikipedia has as the first. That's not usually my source, but I'm curious to what they see as
curious.
Yeah, I'm curious too. I don't know what
it seems to change fairly regularly.
Yes, it does. And so let's talk about gamma ray bursts. What is your studies with these phenomena and what we observe there?
So I'm specifically interested in the types of stars that produce gamma ray bursts. So gamma ray bursts of the type that I am interested in happen when a very massive star undergoes a supernova death, and some fraction of these massive stars will emit beams of gamma rays when they die. What we think is happening is that the star's core is collapsing and producing a rapidly rotating black hole. So that rapidly rotating black hole then effectively consumes the star from the inside. It shatters the star. And as part of consuming the star, you ignite these really high-speed jets that come out perpendicular to the rotational axis of the black hole. Stuff will collide in those jets, and the collisions actually emit gamma rays, and that's what we see as a gamma ray burst. So they're pretty cool. And what I'm specifically curious about is why some stars do this and others don't. And my favorite way of studying that is to look at galaxies where gamma ray bursts have happened and try to pinpoint the properties of a galaxy that allowed a star like that to form. There were ideas about whether gamma ray bursts could only happen in galaxies that had very depleted chemical compositions, that have much fewer heavy elements than our Milky Way. There were ideas that these can only happen in galaxies that are very actively forming stars because we think these stars should be very young, and it looks like that's true. But I will try to study the galaxies where these events have happened in a lot of detail and try to kind of zoom in as close as I can on exactly where the star exploded to see if we can learn a little bit about how the star was born.
Right. So the next question, which I don't see anybody asking, but I get asked it all the time, so I'm just going to go ahead and ask it. What threat do gamma ray bursts pose to Earth, if any?
Awesome question. So the proper answer is probably not much. We're probably fine. But if a gamma ray burst were to go off very close to Earth, like within our own Milky Way, and if that beam of gamma rays was pointed at us, because keep in mind, if the beam of gamma rays went that away and Earth was here, we'd never be hit by the gamma rays. We'd be fine. But if a gamma ray burst went off nearby and it was pointed at us and it would hit us, it would not go well. My understanding of roughly what would happen is that the blast of gamma rays would effectively fry off our ozone. And then life would not go terribly well on Earth. I think I'm not sure the extent to which this is widely accepted, but there was research done, I believe out of Kansas State or University of Kansas, on a extinction that happened. It's at the end of the Ordovician period in Earth's history. And the idea was that extinction could potentially have been explained by a galactic gamma ray burst. Now, I don't think we have any strong observational evidence that we had a gamma ray burst happen that many years ago, or that this is the best or most likely explanation for the Ordovician extinction. But it's a really fun kind of thought experiment to do of what would that do to life on Earth.
Yeah, how frequent are these observations?
Gamma ray bursts are more rare than supernovae. We detect, oh boy, I can't give you a good number right now for how many we detect in a year off the top of my head, but the closest one that we've seen so far was, I think, 40 megaparsecs away. So that's pretty far. And that's part of the question. That's part of why I'm interested in understanding what sorts of stars form these, because we have a very solid understanding of the relative abundance or rarity of different masses of stars. And we already know that really massive stars are very rare. Mm-hmm. When stars are made from a cloud of gas and dust, they form, it's much easier to make small stars like our sun than massive stars like Betelgeuse. But we're trying to figure out what subset of massive stars would make a gamma ray burst. Do they have to be rotating really fast? Do they have to have binary companions? Are there other details? So it could come out that it's very rare to make the sort of star that makes a gamma ray burst, which would make the gamma ray bursts themselves pretty rare events.
Yeah, so I'm going to ask you a basic question again, because I don't know if anybody's going to want to ask this, but I'll do it. So why are they rare? Why are these massive stars rare compared to stars like our own? Why are they not as abundant?
It's a good question. I don't have a wonderful answer for that, and I'm actually not sure astronomers do, because what we know is that when you make a bunch of stars from a molecular cloud that's like 1 million solar masses, you're going to make a lot of stars like our sun and only a few stars like something like Betelgeuse. The physics behind why that's happening is something that people still argue about a little bit, but it's the physics of how you wind up, how that cloud winds up collapsing and forming little proto-stars or pre-stars that then turn into stars makes it easier to make smaller or lower mass objects. So we can actually count up the results of this very well. We can observe very neatly that there are more low mass stars than massive stars. But the full-on explanation as to why and how that might change as a function of chemistry is still something that we're arguing about.
And are there any observable changes in a star that's about to go supernova?
We think so. The problem is we've never looked at one or monitored one right up until the point where it's exploded. We've occasionally gotten kind of lucky where a supernova will go off, and it'll go off in a fairly nearby galaxy that's been, say, well observed by Hubble. And we'll then look and say, it went off in galaxy blah. Hubble just got great observations of that galaxy. Let's go look at exactly where the supernova position was and see if we can spot the star. And this has worked. We've found images well before the supernova went off of stars that have later been proven to have exploded. We'll check again and the star is gone. But all we really see is a picture of it. So we can tell that it's kind of bright. We can tell that it's maybe a certain color if we're really lucky. But we can't monitor its spectrum. We're not monitoring it day by day and saying, it suddenly flared or it suddenly did something else dramatic. And I have colleagues who try and predict what these stars will do, and the predictions are very complicated. What I'm hoping will happen, somebody in the chat mentioned LSST. So this is the Large Synoptic Survey Telescope. Mm-hmm. This is a telescope that's getting built in Chile, and it's going to come online in the very early 2020s. And it's basically monitoring the entire sky every 3 nights and looking for anything that changes. So it is going to be very good at detecting new supernovae. And what we can then do is use LSST to back up and say, what was happening at that position 3 days ago or 6 days ago? Or has anybody observed that star before that we've now realized has just exploded? So hopefully this will help.
Yeah, and there was another one. God, there's so many. Our gamma ray bursts only significant because they are the highest energy light. Are there bursts of other light not in the visible light spectrum?
Yeah. So gamma ray, part of the reason that they're significant is because they're so incredibly high energy and because they're so incredibly bright. We can see gamma ray bursts happening almost across the visible universe. So this is why we're interested in them. If we can explain what type of star produced a gamma ray burst, we can explain what type of star was clearly present across the visible universe if you're looking into the sky or looking back in time. So if you're seeing something that far away, you're seeing something from fairly early on in the universe's history. That's why we're interested in them. We don't typically get bursts just like gamma ray bursts in other wavelength regimes, but we see bursts of light at other wavelengths all the time. We'll see things like solar flares in other stars. We'll see flare stars and they'll get bright in the optical. We'll see flares of X-rays from stars or from binary systems. There's a phenomenon known as fast radio bursts, which are these brief, bright bursts of radio light that we still have not explained. These are huge and really interesting mysteries in astronomy right now. We don't know if those come from stars or what, but we do see flares from other wavelengths, but they're not the same as gamma ray bursts. We're seeing a massive mix of phenomena. Somebody posted, LOL, the universe is bursting, but that's exactly right. Yeah. We think of the sky as very static, and in reality, it's changing very dramatically and very rapidly with time. So this is why something like LSST is going to be amazing, because we're watching it change on the order of like a few days. And I think we're going to discover a bunch of stuff that incredibly surprises us when we turn that telescope on.
Yeah, someone said, aren't cosmic rays slightly higher as far as energy? Yes, and they're not on the EM spectrum.
Yeah,
but you can further elaborate. So aren't they higher? Do we measure those?
I haven't studied cosmic rays at all. Actually, cosmic rays are annoying to me because once in a while a cosmic ray will hit the detector of a telescope and it shows up as this bright thing and you have to get rid of it. But I was restricting my answer to the electromagnetic spectrum, which is what I observe and what we're typically observing from objects like this. If you think about cosmic rays, or you think about neutrinos, there's a whole other area of space physics that we can get into that's fascinating. But in terms of electromagnetic radiation, gamma rays are the top end of the spectrum.
Someone said, do you know how gamma rays affect the brain? We know that it's not good to your DNA.
I don't, yeah, I think badly.
We can just say it's not good. You see what happens with ultraviolet radiation, no bueno. And you can assume anything that's a little bit more higher energy.
Somebody who knows more superhero lore than me can help. Isn't this the Inception story for the Hulk?
Yeah, it is the Hulk.
Was it gamma rays? Okay.
Yeah. And that's why I love
very
it when
scientific.
They work. It is. It's so scientific. I mean, at least they're trying. At least they're trying to make it relevant to pop culture. That's where I get very excited about that. Gamma rays are bad. Yeah, cosmic radiation is also no bueno. So you don't want to be exposed to anything ultraviolet, really. X-ray. There's a reason that you have to be protected when you get an X-ray. You know, and that's a very small amount of that radiation, very, very limited amount. So yes, anything that's very high energy on the EM wavelength, no bueno. Someone said, does solar wind from an emerging star push away a significant amount of stuff that might have been a part of the star's mass otherwise?
Solar wind from, did you say an erupting star?
I'm going to assume yes.
Yeah. So the wind from a star it's actually it's a similar idea to the kind of wind that you would just have like in a room. Like if I were to open the window in this room, I'd create a pressure differential in the room and stuff would flow toward the lower pressure area. So you get a pressure differential from the inside to the outside of the star, and you actually get a particle radiation flow or a particle flow out of the star. That wind on its own will wind up sweeping up and dragging along gas in the star, and that's how you wind up losing mass via a solar wind. If a solar wind is really strong, then yes, you can see it affecting the shape of the area right around the star. And we wonder about things like this when you say have two stars in a close binary that both have strong winds and what their winds are doing to one another. But it wouldn't full on like blow away the material of the star. It would just blow it out to a slightly larger radius.
Interesting. So another question that actually I was trying to look for something on it online, and I think it was Phil Plait that described it, but I wanted to hear your take on this. Mm-hmm. How fast does the fusion happen with these higher mass stars, the heavier elements? I know the fusion starts to get pretty insane in terms of how fast it actually occurs with these higher mass stars towards the end of their life. Yeah. Do you want to blow people's minds with how fast some elements are fused?
Yeah. So if you were to slice open a star right before it died and sort of look at the cross section, it would look like it was made up of layers like an onion. And those layers would be a nice guide to what we've been fusing in the core of the star. So an outer layer would be hydrogen, and these stars fuse hydrogen for 8 to 10 million years-ish. And then helium, which is fused for maybe a couple million years. And then you would go on to heavier and heavier elements. And by the time you get to silicon, which is about the last thing that a star can use for fuel to create energy that counteracts the inward press of gravity, these stars burn silicon for like 2 days before they die. Because eventually you go from, the next step after silicon is you wind up trying to fuse iron. And this goes very poorly for a star because fusing iron actually requires energy, whereas everything else that they've been fusing so far produces energy. This means that gravity wins and the star collapses, and we get this explosion that we see as a supernova. But the preceding step of that, silicon burning, is 2 days in length. And there's been some fun debate about this. I mentioned that I have a colleague that's working on modeling what these stars do right before they die. And I've seen data on, what does a star do while it's burning silicon? And it looks like a modern art plot because they're just imagining like how the temperature is changing and how the luminosity is changing, and the star's just doing this. Like, it's incredibly hard to predict. But we've never observed a star directly like that 2 days before it's exploded. So we don't have a great test bed for that. We just know that it should be very dramatic when it happens.
Yeah, so 2 days, guys, 2 days. That's insane considering, these lighter elements that it starts fusing. Like our star, is doing that hydrogen to helium still. So, and so crazy. So can a crazy dense and hot star actually fuse iron? Someone asked. Iron's the limit.
Well, You could try to fuse iron, but the problem is doing that requires energy. So the reason that stars are able to stay stable is you have fusion happening in the core, and that is able to create an outward sort of counterbalance to gravity, which is permanently trying to collapse the star. So if you lose that outward press from the core, then gravity wins and the star collapses. So that's why we don't just wind up with big iron balls at the end of a star's lifetime for a star like Betelgeuse or like a massive star. In that case, the core of the star implodes, and that whole implosion takes less than a second. And it winds up imploding into something like a neutron star or a black hole. And the outer layers of the star come tumbling down after it. They bounce off of the neutron star or the temporary halt to that collapse that's happened. And the bounce back gives you the shock wave that you see as a supernova.
Someone said, can binary stars fuse iron using their sibling star?
No, not that we know of. Both of those binary stars, well, hang on. They can't fuse iron when we talk about fusion, that's not what we see happening. Both of those stars still have to maintain their balance, so you won't have one of those stars fusing iron in a core. There's other processes, we call them nucleosynthesis processes, that happen in stars. So this isn't fusion in the traditional sense where you just crank up temperature and density really high and fuse hydrogen atoms to make helium or something like that. But you'll have other chemical reactions going on in stars, and that can involve much heavier elements. So you can wind up with elements like molybdenum and gold and krypton and like all these relatively obscure elements that you would actually see in stars because of those other processes happening. And you don't need a binary companion for that. This is just something that happens in the outer layers of stars when you're throwing protons and neutrons around with a bunch of atoms. It's kind of the inevitable result.
So are there any massive stars that are currently being observed, like that are forming right now?
So even the process of forming a star takes millions of years, so we can't actually watch one being formed. What we can look at are very young massive stars that we think were only born in the past 1 or 2 million years. One project I'm working on right now with some collaborators is studying a galaxy that we think is really, it's mainly made up of stars that are very young that we think were born only a couple million years ago. So there's kind of the fun question of, well, should we just stare at that galaxy until something dies? But most of these timescales are really long. Like a star that was born 2 million years ago might still need another 1,000,000 years before it explodes. So we could wait, but it's going to be a while.
It's going to be a while. We might not be around. We might have to hand this project off. So as far as like how these new, do you study any of the, and I believe you do, like some of the first stars that were created in the universe, like some of these, anybody, you can just run with it.
I don't directly study these. I study them in that I'm interested in gamma ray bursts that are happening well across the universe. So when a star like that explodes, we're seeing the explosive death of something that was similar to the very first stars in the universe. So I'm interested in that because those explosions give us a hint of what the first stars in the universe would look like, but I don't directly study them. The chemistry of those stars is really fascinating, and I have colleagues who do, but it's not something that I quite work on myself.
Yeah, and someone actually asked about the chemistry with astronomy and what people could do if they had an interest in chemistry but wanted to maybe get into the astronomy field.
Oh, there's a subfield called astrochemistry that is specifically focused on, studying the exact chemistry of stars, of the interstellar medium, which I know sounds boring, but knowing exactly what the chemistry is of the dust in space and the interstellar material in space is unbelievably valuable if we want to, look through it or study it itself or study the stars that form from it. So yeah, astrochemistry is a really interesting field.
These are 2 questions, and then we can start wrapping up here because I know it's getting close to the hour. And thank you again so much for taking the time.
Yeah, thank you for having me. This is always really fun.
I know it's a lot of questions, so I understand. Like, if there's things you don't know, it's like completely fine because I say I don't know all the time. It's wonderful. People love me for it.
Please don't ask me about planets.
I know. I've seen some
specialty
people,
at all.
Yeah, people have asked about Ganymede and
fascinating, but I don't know.
Very fascinating, but yeah, there's a reason that we have people that go and get their degree in specialized because we need that. Someone said, when modeling giant stars, do you guys use Newtonian gravity or GR?
Ooh, when we're modeling the star itself, we stick with basic Newtonian gravity. When we start looking at things like what a black hole companion would do to a star like that, or how the star goes from a normal star to a black hole, then we do have to start considering relativity, and those models get complicated but fascinating. But for modeling just a regular star and how it works, normal treatments of gravity are fine.
There you go. And then I think I've asked you about this before. What about blue stragglers?
Oh, yeah.
Yeah.
So what a blue straggler is, and somebody else was asking how we can tell that stars evolve. So this kind of answers both questions at once. We can look at clusters of stars that we think were all born at the same time. And if we can estimate how old the cluster is, what you get is a snapshot of how stars at different masses have evolved. A star that's really massive doesn't live that long. A star that's less massive will live a really long time. So we'll get a snapshot of, oh, the stars that are like our sun are at a sun-like point in their evolution. Stars that are a little more massive or now look like red giants. Stars that are a little more massive than that look like asymptotic giants, which are more extreme versions of red giants. And it gives us a little freeze frame of what stellar evolution would look like. And what we know is that stars will start off fairly hot, and then when they run out of hydrogen to fuse in their cores, they start cooling off. And this should be really linear. Like as the cluster gets older and older, stars at lower and lower masses should one by one run out of hydrogen to fuse in their cores and start cooling off. You occasionally run into these stars called blue stragglers that appear to have defied this rule. They should already be evolving into the red point of their evolution, and they have not. And they're called blue stragglers because they look unusually blue for how they should appear. What we think is happening is that the best explanation that I've gotten for these, and I don't directly study these, but the best explanation is that their evolution has been messed up by binary interactions or other disruptions from stars near them in their cluster. But I know that this is an area that people are still working on.
And would those stars that we know as Wolf-Rayet stars, would those fall into some of the blue straggler category?
So Wolf-Rayet stars are actually much more massive. Blue stragglers are stars. They're similar to our sun in mass. They're maybe a few times the mass of our sun. They're billions with a B of years old. Wolf-Rayet stars are stars like Betelgeuse. So they're maybe a few million years old. And those actually look blue for a completely different reason. If you had something like Betelgeuse, a star that's a red supergiant, and it starts losing a lot of mass, either because its wind is carrying mass away or because a companion to the star is dragging mass off of it, you'll actually start peeling off the outer layers of the star. You see deeper into the star where it's hotter, and the star goes from appearing red to appearing blue. So that's what Wolf-Rayet stars are. We think that Wolf-Rayet stars are the stars that should produce some types of supernovae and maybe gamma ray bursts, although we still haven't proven that. But they're fascinating stars.
Yeah, in and of themselves, those are a whole different category. I know I have a lot of people talking about those. But yeah, they're not as luminous, though, as like, no, they're very luminous because they're also massive. But as these blue stragglers, they're not as luminous because they're not as massive, right?
Right. And we think what's happening to them is something different. I don't think the theory is that they've been like peeled to look bluer. I think that the interactions with other stars in the cluster have disrupted how they would normally evolve.
Interesting. That's so interesting.
It's so weird.
Because there's so many things. I have so many people that want me to just talk about them. And I'm like, guys, like there's so much I don't know about that level of stellar evolution that goes so deep in and of itself. Well, someone said, why stars die and not just turn into big iron balls?
Yeah, no, I think I saw a similar question to that before, and I just answered it. That for a star like our sun, we actually never really see iron come into play. A star like our sun will fuse hydrogen in its core, then it'll fuse helium in its core, and then its core will form something called a white dwarf, which is a star that's actually supported by a principle of quantum physics called electron degeneracy pressure. We're basically squeezing the electrons and the atoms in the core of that star together so tightly that they start resisting an inward pressure because they would start violating rules of quantum physics. So that's what would happen in the core of our sun, and then the outer layers of our sun would slowly get puffed off. You'd be left behind with a white dwarf, and it would just sort of fade away. For a massive star, when you wind up with that iron core, there's so much junk on top of it from the rest of the star that core actually collapses, and it makes a neutron star or a gamma ray burst. So the iron core just can't happily sit there and not do anything. It winds up collapsing.
And someone just said, and I get where this is coming from, can white dwarfs reignite?
God, you have no idea how timely this question is, because I'm teaching our graduate class on stellar evolution right now, and we were just talking about white dwarfs. Reignite is a complicated term to use. You won't, for example, see a star that became a white dwarf that then gathers material back around it and turns back into a normal looking star. Typically what will happen to a white dwarf is it'll either happily go along, not bothering anybody, or if it has another star as a companion, it will slowly accrete mass from its companion. Eventually, you will wind up igniting sort of a runaway thermonuclear detonation on the surface of the white dwarf, and it explodes as a different type of supernova than what I've been talking about. So this is specifically a white dwarf produced supernova, and that just blows the star up. This isn't collapsing into a neutron star or a black hole. The star just... So maybe that's probably our closest thing to what it looks like when a white dwarf reignites.
So reigniting, just to be clear, you wouldn't be saying it would become another, a star that would be able to fuse again.
No, it wouldn't become a star that could fuse again in its core, nothing like that.
Right. So I'm just making sure everybody in chat understands that. And I think actually that is good. That is 7:30. That is an hour, guys. But thank you so much for coming on. I appreciate it, guys. All of the stuff is listed in that guest link that you can find all of her information. She does have a lot of really interesting Twitter stuff, especially about spiders. And you guys can
spiders
actually
and
go
astronomy.
Yeah. Right. And again, I will link the video to her latest talk at the Perimeter Institute. It is so good. If anybody hasn't watched it here on my stream, we're probably going to rewatch it again later and later. We just do that a lot, but thank you so much for taking the time, and hopefully we can catch up again soon.
Yeah, no, thank you. This was really fun. I would love to come on again.
All right. Thanks so much. Have a good night.
Thank you. You too.
All right,
bye, everybody.
Let's see here. We good.